What is a matrix? The traditional notion of a matrix is a two-dimensional array with numbers in it, like this. This has two rows. The first row is 1, 2, 3, and the second row is 10, 20, 30. It also has columns. So the first column is 110, second column is 220, third column is 330. We call this a 2 by 3 matrix. For matrix A, the ij element of A refers to the element in row I, column j, and it's usually written A subscript ij. We'll sometimes use the more Pythonic notation A brackets ij. And here's an obvious representation for a matrix. We can represent this matrix by a list of lists. Each element of the top level list is a list consisting of the elements of a row. So the first list is 1, 2, 3, the first row. The second list is 10, 20, 30. You could similarly represent this by a list of column lists, where there's one element of the top level list for each of the columns of the matrix. I'm going to take a slightly different approach to matrices. For finite sets R and C, an R by C matrix over a field F is a function from the Cartesian product of R by C to the field F. So here's an example. A and B are row labels, and @ sharp and question mark are column labels. And in Python, we'd represent this as this function as a dictionary mapping from the Cartesian product, the set of pairs, one element from R and one from C, to the field. And we can represent this by a dictionary. For this matrix, the row labeled by A is the vector with domain @ sharp and question mark, mapping @ to 1, sharp to 2, and so on. And the column labeled by sharp is the vector with domain A and B, mapping A to 2 and B to 20. Here's one representation for a matrix as a dictionary of rows. It maps each of the row labels to a vector that is that row. So in this dictionary, the row label A maps to the vector 1, 2, 3, and maps B to the vector 10, 20, 30. A similar representation is as a dictionary of columns. Here the dictionary maps the column labels to the vectors. So @ sign is mapped to 110, sharp is mapped to 220, and question mark is mapped to 330. Our primary representation for matrices will be using a Python class mat. This is a class with two fields. This is analogous to, but not exactly like, vec. The two fields are D and F. F, just as in vec, is a dictionary. D is, instead of being a set, a pair of sets. You would think that D would be the set that's the Cartesian product of the row labels with the column labels, but that gets too big. So we represent it as a pair, RC, where R is the set of row labels and C is the set of column labels. F is a dictionary that maps elements of the Cartesian product, pairs, row label, column label, to the corresponding field elements. And of course, our sparsity convention is used here, so we don't have to represent entries of the matrix whose values are 0. So here's a rudimentary implementation of that class, mat. We'll later add lots of matrix operations to this class. To exercise our understanding of the mat class, we'll look at the identity matrix. For a set D, the D by D identity matrix is the matrix such that the KK element is 1 for every element K of D, and all the other elements are 0. I'm going to use the numeral 1 to indicate the identity matrix with a subscript of D, but very often we'll just omit the subscript when it's clear what domain is intended. Very often the letter I is used to represent the identity matrix instead of this numeral 1. So, for example, here's the identity matrix on the set consisting of A, B, and C. The set of row labels is A, B, and C. The set of column labels is also A, B, and C. And the dictionary F maps AA to 1, BB to 1, and CC to 1. We're omitting all the other entries because their values are all 0. We're exploiting the sparsity convention. Now, as a quiz, write the procedure identity of D that returns the instance of MAT representing the D by D identity matrix. Here's the solution. We can convert between our different representations of matrices. For example, consider this matrix. Here's the representation as an instance of MAT. And we can convert this to a column dictionary, that is, a dictionary whose keys are the column labels and whose corresponding values are the vectors that are the columns. Now let's look at converting an instance of MAT to a column dictionary. Here's an example of an instance of MAT, and here's the corresponding column dictionary. Write the procedure MAT to COLDICT that, given an instance of MAT, returns the column dictionary representation of the same matrix. Here's the solution. We provide a module, MAT-util, that defines various conversion routines, such as MAT to COLDICT, MAT to ROWDICT, COLDICT to MAT, ROWDICT to MAT, and list to MAT that converts from a list of field elements to a matrix such that the inner lists are the rows of that matrix, and also the identity procedure that you wrote. I should note that COLDICT to MAT and ROWDICT to MAT can take as arguments a COLDICT, a column dictionary, or a row dictionary, or a list of columns or a list of rows. So it's somewhat more flexible. Now, we gave the definition for a rudimentary matrix class, but we're going to write a much more elaborate one that incorporates all these different operations. And here's the syntax for each of them. This more elaborate class definition allows us to write much more concise matrix and vector code, such as this. This sets the entry corresponding to row label A and column label uppercase B to 1. This assigns to the variable B the vector obtained by multiplying the matrix M by the vector V. This assigns to the variable B the matrix obtained by multiplying the matrix M by the matrix A, and this pretty prints the matrix B. You'll learn more about these operations as we go on. So you're going to code this class starting from a template we provide. As in the case of VEC, you're going to write the bodies of name procedures. But in using MATs, you're just going to use the operations, as we described here. This is a much more concise way of writing than this. So in all code outside the MAT module that uses MAT, you're going to import just the class MAT itself using this command. So the name procedures are not used. They're not even imported. In short, use the operators and the method transpose defined in the class when working with MATs. For each procedure, just as in VEC, we'll provide the stub. As before, you're going to replace the pass statement with the appropriate lines of code. As before, the first line is a documentation string. The second line is an assertion. In this case, it asserts that the second element of the D field of M has to be a set that's equal to the domain of the vector V. If this assertion is violated by the arguments, Python will report an error. So this assertion is there to remind us of a rule about, in this case, matrix vector multiplication. So please keep the assertions in your code when writing code for this class. Again, we're going to be using MAT a lot. We have to make sure that your MAT implementation is correct. So we've provided a file, testmat.py, with lots of examples to test against. So you should make sure that your MAT implementation works for all these. As before, you can copy the test in from test.mat, or you can run all the tests at once using this command. If it doesn't print anything, all the tests are passed. One simple rule for matrices is as a way of packing together a bunch of rows or a bunch of columns. We define two vector spaces for each matrix M. One is the column space, which is the span of the columns of that matrix M. The other is, and it's written col M. The other is the row space of M, which is just the span of the rows of M, and that's written row of M. So for example, the column space of this matrix is the span of its columns. The first column is 110, second column is 220, third column is 330. Now in this case, the span is just equal to the span of the first column, 110, since the other two are scalar multiples of that. But similarly, the row space of this matrix is the span of the two vectors 1, 2, 3, and 10, 20, 30. And again, this is also equal to the span of just the first vector, 1, 2, 3, since the second one is a scalar multiple of that. Transpose swaps rows and columns. So if you start with this matrix, where the row labels are A and B, and the column labels are at, sharp, and question mark, you apply transpose, you get this matrix. So for example, the entry in row A and column sharp of the original matrix is the entry in column A and row sharp of the transposed matrix. Pretty soon we'll explore the operations on matrices, but first let's note that a matrix can be interpreted as a vector. After all, an R by S matrix is just a function from the Cartesian coordinate R cross S to the field F. So it can be interpreted as an R cross S vector. Thus, we can do scalar vector multiplication and vector addition. And our implementation of matrices will incorporate those operations.